And we're back. Welcome back and happy Thursday. Today, we will resume our discussion of the geometric distribution. The reading by the 13th, which was past Tuesday, is sections 3.3 to 3.4, pages 47 to 67 for this material. So last time when we met, we talked about the geometric distribution and we developed the probability mass function, the probability that the first success occurs on the xth trial from a sequence of trials is 1 minus p to the x minus 1 power times p, where p is the probability of success on a particular trial. And in this discussion, we talked about this geometric distribution as being a sequence, a particular sequence of Bernoulli trials, where you have a sequence of failures where trial number X ends in a single success. And so we set out to show that it is in fact a probability, even though it's an infinite series. And this is the so-called geometric distribution because it is governed by the geometric sequence or series. And so we took a brief detour describing the geometric series. And for the geometric series where we last left off, let me set my pen here. We'll pick blue. We said the geometric series is a progression, a sum, where each successive term is calculated by taking the previous term and multiplying by a constant factor we called r. And we will show, was where we left off, that this series for the first n terms, so here's the 0th term, the first term, up to the n minus 1th term for a total of n terms equals this closed form expression. K goes from 0 to n minus 1, a times r to the k power. And what we set out to do is to show that if we can do this for n terms, we can do it for n plus 1 terms, which ends in an n, a times r to the n power. And then to show that the infinite series converges to a closed form expression, we just show for these n minus 1 terms, a up to a r to the n power. And then we just let n go to infinity through the limit. Okay, so let's continue. So we set a sum for the first n terms. So here's AR to the n minus 1. We call that S. We multiplied both sides of the equality by a constant factor R. We got RS equals AR squared, AR cubed, and so forth. And then we subtracted this second form after we multiplied left and right for the first equation by constant factor R. We subtracted that second expression from the first expression. So, of course, we made the observation that here on these diagonal elements, we have the same term in a different position in our original sum versus the augmented one where we multiplied both sides of equality by r. And so when we do the subtraction, well, AR is going to subtract, go to 0, but what we're left over with, and all the other terms are going to subtract, we're left over with this A term, and we're left over with this AR to the n term, but that's subtracted. So on the left-hand side of equality, we have S times R minus S. On the right-hand side of equality, we have A minus AR to the n power. So we factor out a common S from the left-hand side, so it's S times quantity 1 minus R. We likewise factor out an A from the expression on the right-hand side of equality, that's A times 1 minus R to the n. And now we divide both sides of equality by 1 minus R. So we do that, and we pick back up doing that division, and we get a closed form solution for the sum for the first n terms is equal to A times 1 minus R to the n upon 1 minus R. So we have that closed form expression for that particular sum of the first n terms in this geometric series. And so we're going to make a little bit of a limitation. We'll notice that, this denominator, if r is 1, this goes to infinity. That's a little bit of a problem. Oops. So mathematically, we're going to say, okay, this works, except for when r equals 1. So we're just going to ignore that case where this blows up. So we're going to say this holds true, absolutely, but r is not equal to 1. So we avoid that issue. All right. So now what we're going to show is we're going to show that this geometric series for an infinite number of terms, before we had the first n terms, where the highest exponent here was r to the n minus 1 power, now we're going to show the infinite case. And how we're going to do this, we're going to show that for this infinite series, it's equal to closed form a times 1 upon 1 minus r for this special case where r, a constant factor, its magnitude is less than 1. Now, one of the things we're going to make an observation about that we just got done doing when we had that sequence of the first n terms, we got the following expression. We had that sum where k goes from 0 to n minus 1, ar to the k power is equal to closed form solution a times 1 minus r to the n upon 1 minus r. And so one of the observations that we're going to make is that in this closed form expression, the exponent for this r to the n, that n, is always 1 more than the upper bound of the summation index. The upper bound of the summation index is n minus 1. The exponent for that numerator is r to the n, it's to the n power. So we're going to notice or remember this fact. And so what does this mean? What it means is that now let's set a equals to 1, because it doesn't really matter what a is. We're just going to talk about the constant factor. And so if a is equal to 1, if we consider the infinite sequence, well, really, that's just a sequence of the first n plus 1 terms, right? That's 1, r squared, r cubed, up to including r to the n power. So if we had r to the n power, well, these would be n many terms plus 1. So that's n plus 1 terms. And so in order to show the infinite series case, we let the largest term in this geometric series have that exponent n, and then we just solve closed form for that, and then take the limit as n goes to infinity. All right, so let's go ahead and do that. So we take that series, and we use this observation that we had, where here, if we have the highest index of the summation is n minus 1, then that power is going to be 1 more r to the n. So here we have this sum, k goes from 0 to n. N is the highest index of the highest value of the index for that summation. So we're going to say a times 1 minus r to the n plus 1 power. N plus 1 is 1 more, right? So this is 1 more than that upper limit for the index for the summation. So it's a times quantity 1 minus r to the n plus 1 power upon 1 minus r. So now we're going to take this expression. And this, remember, in this expression, we said for r, magnitude is less than 1. And we're going to take the limit as n goes to infinity for this closed form expression. So what's going to happen? Limit as n approaches infinity of 1 minus r to the n plus 1 power upon 1 minus r, well, is nothing more than 1 over 1 minus r. So why is that? Well, if r is less than 1, each time we multiply something less than 1 by itself, it gets smaller and smaller and smaller and smaller and smaller. So we could see this if you had 0.1, you multiply by 0.1, it's 0.01, multiply by 0.1 is 0.001. And if you do that n many times, as n goes to infinity, well, this term goes to 0. So if it goes to 0 in the limit as n approaches infinity, well, that means you have 0 here, you have 1 over 1 minus r. So that's our result. So the sum for the geometric series, where it's an infinite sequence, that closed form solution is just 1 over 1 minus r, provided that the magnitude of r is less than 1. Now, of course, that magnitude of r less than 1, it kind of fits in our case. Probabilities satisfy this property. A probability, we said, is drawn from the closed interval between 0 and 1 on the real number line. So absolutely, a probability fits that criterion, less than 1. Okay, so now that we have this fact, let's go back to our geometric series. We had set out to show that the law of total probability holds true. So let's build a geometric sum, and this is our total probability. We're adding up the probability mass function. There's our probability, 1 minus p to the x minus 1. Those are x minus 1 failures ending in a single success at a rate of p. And we're going to sum all of those for all possible values of x, all places in line where that single success can occur. So if we do that sum, we want to show that the probabilities all added up for all positions x in line, it sums to 1. And so we're going to treat this as a geometric sum, and as a geometric sum or series, if we call the a term our scalar, if that's p, and then our constant factor r, that's 1 minus p, which is also nicknamed q, then we just look in the limit as n approaches infinity what that series is in closed form. So this is just going by our scheme. We have a, or p, times 1 minus, here's our r to the n plus 1 power over 1 minus r. Okay, so we get 1 minus quantity 1 minus p to the n plus 1 power upon 1 minus quantity 1 minus p, all of that times p. So we're going to take the limit as n goes to infinity for this expression. And that's exactly equal to 1. Why? Well, 1 minus p is less than 1. And so if we do this 1 minus p to the n plus 1, that goes to 0. And so that's 1 over 1 minus 1 minus p. So that 1 over 1 minus 1 plus p, or if we expand out the denominator, all that times p. Well, 1 minus 1 is 0 rather. This goes to 0. That's 1 over 1 times p. That's just p over p. All right, so this denominator is 1 minus 1, that's 0. That's plus p. So we have, that should be plus p. 1, let's try this again. So if we plug in for what our constant factor r is, we have 1 minus 1 quantity 1 minus p to the n plus 1, so that's r to the n plus 1, upon 1 minus r, so it's 1 minus quantity 1 minus p, all of that times p. And so if we take the limit as n goes to infinity, well, this is a probability. Well, this is a probability, and it's as a probability, it's less than 1. And so in the limit, it goes to 0. So this term is going to go to 0 as n goes to infinity. So we're left with 1 over 1 minus p, all times p. So if we look at the denominator here, well, that's 1 over 1 minus 1 plus p times p. The 1 minus 1, that goes to 0. We're left with p over p, which is just 1. And so this infinite series, that total probability is equal to 1. And we've proven, yes, this does act like a probability, even though this is an infinite sum. Okay, so let's look at the summary statistics, and this is from the book. And we're going to look at the mean, and we're also going to look at the variance. Now, with the mean, they start out taking the geometric series. Here's our sum, and q, it's a geometric series defined by constant factor q. And here we have the sum, and we showed that it's 1 over 1 minus our constant factor. Now, we've been calling it r when we talked about the geometric series, but in the book they call it q. And so we're going to start out taking the derivative of this series, and we're going to do it two different ways. One way we're going to do it is we're going to take the converged closed form form solution for the series. And we're going to take the derivative of that, and that's in this direction, going to the left. And then we're also going to take the formula for that infinite series and take the derivative, and that's going to the right. And we're going to use this quantity, the derivative of the closed form solution, and this quantity, the derivative of the series itself, as a substitution to help us solve for the expectation. And then we're going to do that with the second derivative and use that to help us with the solution for the variance. And so let's take a look at the expectation. This is our setup for the expectation. Expectation, E of x, is nothing more than the weighted sum for all values of x goes from 1 to infinity, of x times the probability of x. Okay, so let's first do our derivative for the series on a blank sheet, and we'll show this derivative both in terms of the derivative of the sequence by showing the derivative of the closed form, as well as the derivative of the original series, its formula, and then we're going to use that substitution to help us with the expectation. All right, so why don't we begin? So we have S of Q, and that's going to be our series. And our series, we said, is just the sum, infinite sum, for x goes from 0 to infinity. Let me make sure this pen works. 0 to infinity of q to the x power. Now, we just said that's equal to 1 over 1 minus q. Right? That's what we showed when we talked about the geometric series. So now we're going to compute the derivatives. We're going to say dq, the derivative with respect to q, of our series S of q, it's going to be equal to two different things. It's going to be equal to the derivative, ddq, of the original expression for the series, ddq of our infinite sum, x goes from 0 to infinity, q to the x power. And that's also going to be equal to ddq, our derivative with respect to q, of our closed form solution, 1 on 1 minus q. Okay, so we're going to show both of these. So we're going to start out and we're going to show ddq of this closed form solution. So let's do that. All right, so the first thing we're going to do is we're going to say let u equal 1 minus q. We're going to do a u substitution and compute the Jacobian. And so that means du dq is equal to minus 1. We're just taking the derivative. And so the chain rule says, chain rule of differentiation says if you want to compute the derivative of some function with respect to q, ddq, that's equal to, if you had an intermediary with respect to some other variable, d du, in terms of u, times the rate of change, du, with respect to q, dq. All right, so that means if we rewrite this expression, 1 over q, we can compute the derivative using this u substitution, and this Jacobian is this factor, du dq, that's going to help us to compute this derivative more easily. All right, so why don't we do that? So if we substitute, well, we say ddq of that substituted version, that's u to the minus 1, right? So if u is equal to 1 minus q, 1 over 1 minus q is equal to 1 over u, which is u to the minus 1 power. And so that's going to be equal to, well, du times, by the chain rule, du dq of this u inverse. Okay. And so what does that give us? Well, ddu, well, that's just minus 1, right? That's the d du. That's what we said before from the u substitution, du dq rather. That's minus 1 times d du. So du dq is minus 1. So we have minus 1 times d du of u to the minus 1 power. Okay, so that's nothing more than minus 1 times negative u to the minus 2 power. Well, minus 1 times something negative, that's just u to the minus 2 power. And we substitute back in for u, and that's equal to 1 over 1 minus q quantity squared. Okay, so that's going to be our derivative of the closed form solution for this geometric series, this infinite sum. Now we're going to look at the derivative of the formula. And so we said d dq of s of q. Another way we can write that is just s prime of q, right? That's equal to d dq of our infinite sum. X goes from 0 to infinity, q to the x power. Okay, so now if we do this derivative, well, the derivative of the sum is the same as the sum of derivatives. So that's just the infinite sum. X goes from 0 to infinity, d dq of q to the x power. Well, that's nothing more than our infinite sum. X goes from 0 to infinity of x times q to the x minus 1 power, just by the rule of differentiation. So what that means then, and we take those two things, well, the closed form derivative, that's 1 over 1 minus q squared, quantity squared, and the derivative with respect to q of the formula for the series is xq to the minus 1. So that means wherever we see a 1 over 1 minus q quantity squared, we can also write infinite sum x equals 0 to infinity of x q to the x minus 1 power. Okay, so now we're going to use this. We're going to use this to show the expectation and actually solve for the expectation. And so this expectation, we said e of x, and e of x substituting is just the sum for all values of x, and it's going to be an infinite series. X goes from 0 to infinity, and that's just x times the probability of x. Well, we just got done saying that the probability, we know what that is. So let's substitute for the probability mass function for p of x. That's just the sum. X goes from 0 to infinity of x times q to the x minus 1 times p, because that's the probability of the xth trial in that sequence of Bernoulli trials. The xth trial is the single success after a string of failures. Okay, so this is going to be our expression for the expectation. And if we look at this summation, well, the index is x, and so p does not involve x anywhere. So we're going to factor p out from underneath that summation. So we say p times the sum, x goes from 0 to infinity of x times q to the x minus 1 power. Now that's where our identity comes in. We have an x times q to the x minus 1 power, and we're going to multiply all of that by our p. So guess what? Look, we have x q to the x minus 1 power, infinite sum from x goes from 0 to infinity. We're going to rewrite this using this substitution. So we're going to write p times 1 upon 1 minus q quantity squared. Okay, so now we know for probability, we said p is equal to 1 minus q. We have a 1 minus q here in the denominator. So we're going to write p times 1 over p squared. Well, you have p in the numerator, you have p squared in the denominator. That's just equal to 1 over p. And therefore, our expectation, e of x, for a geometric random variable adhering to the geometric distribution, our expectation is just 1 upon p, or 1 over p. All right, so that's our expectation. Now, we had an expression for our first derivative for the sequence, and that first derivative, we said s prime of q, we solved for that, is equal to 1 over 1 minus q quantity squared. To take our second derivative, what are we going to do? Well, we also said, let me first finish this thought, is equal to the sum of, from x goes from 1 to infinity, of x times q to the x minus 1 power. Okay, so we did that, and that was our first derivative, and we used it for our expectation. So now we want to solve for the second derivative. We want to solve for s double prime of q. Well, that's nothing more than d dq of that closed form, 1 upon 1 minus q quantity squared, as well as d dq of that summation form, the formula, sum for x goes from 1 to infinity, x times q to the x minus 1 power. Okay, so now if we look at our closed form solution, we're going to do a u substitution, and we're going to use the chain rule, solve for the Jacobian. And if we do that, I'll leave that as an exercise to you. You get 2 over 1 minus q quantity cubed. Okay, and if we take the derivative of this expression, this formula for the series, that's equal to, that's the infinite series, sum, x goes from 1 to infinity of x times x minus 1 times q to the x minus 2. Now we can further reduce this expression. We can carry out this multiplication, and if we carry out this multiplication, we get the following. We get x, the infinite sum, x goes from 1 to infinity of x squared minus x, all of that, times q to the x minus 2 power. Now, if we further carry out this multiplication, we have infinite sum, x goes from 1 to infinity. We have x squared q to the x minus 2 power minus the infinite sum, x goes from 1 to infinity, and we have an x times q to the x minus 2 power. Okay, so now if we do this, we can kind of collapse this, and we know that 2 over 1 minus q quantity cubed is equal to this right-handmost part of equality, sum x goes from 1 to infinity of x squared q to the x minus 2 power minus x goes from 1 to infinity x q to the x minus 2. So now what we're going to do is we're going to take this minus term and we're going to add it to both sides of equality, and this is going to give us an expression for this first term. And so that becomes the sum, x goes from 1 to infinity, x squared q to the x minus 2 power is equal to, we have 2 over 1 minus q quantity cubed plus infinite sum, x goes from 1 to infinity, x times q to the x minus 2 power. So all we've done here is added this expression, that minus term, to both sides of equality. And so we're going to use this right-hand side as a substitution for this in helping us to solve for the variance. So let's do that. We can further reduce. Let's further reduce it first. So we have this expression, and we're going to take this expression and we're going to manipulate it a little bit and come up with a much simpler version of this term. So let's do that. So we have our infinite sum, x goes from 1 to infinity, x squared q to the x minus 2 is equal to, we have 2 upon 1 minus q, quantity cubed, plus, now when we see this, we want to make use of what we had when we took the first derivative. But we have a problem here. This q has an x minus 2 power. We want to make an x minus 1 power. So how we're going to do that is we're going to pull out a factor of q. So we're going to write 1 over q times that sum, x goes from 1 to infinity, of x times q to the x minus 1 power. And we can absolutely do that, because if you had 1 over q times x times q to the x minus 1 power, well, that's just the same as saying q to the minus 1 power times q to the x minus 1 power, right? These powers add. So that's q to the x minus 1 power, which is just q to the x minus 2 power. Okay, so if we do that, now we can take advantage of our result that we had when we took the first derivative of the sequence. So we do that substitution, and so we're going to take this term and we're going to substitute in what we know from that first derivative of the closed form expression for the geometric sequence. So if we do that, we have 2 over 1 minus q to the 3 power plus 1 upon q times, and we just make that substitution, 1 over 1 minus q. Okay, so now that we've done this, it's just a little bit of algebra. And so with this algebra, we're going to multiply this q by that denominator. So that's 2 upon 1 minus q cubed plus 1 over q times 1 minus q. All right, so now we're going to do lowest common denominator. And so we have a q over here. So that's 2 times q over q times 1 minus q quantity cubed. And then if we want this other denominator to be the same, well, we have a q, we have a 1 minus q, we need a 1 minus q. Something, oh, no, you know what? This is that should be squared. There we go. That should be squared. All right. So we have this 2 over 1 plus q cubed plus 1 over q times 1 minus 2 squared. I had the substitution wrong. So here now, we have our common denominator, q times 1 is q cubed. To get that, so we multiply this numerator by q. That's 2q. And then here, we have a q and a 1 minus q squared. We need it to be 1 minus q cubed. So that's going to be plus 1 times a 1 minus q. Okay, so now if we do this, what do we get? We have a 2q plus 1 minus q. That's going to be equal to 1 plus q in the numerator, and we're going to have q times 1 minus q in the denominator. And so we can substitute then our infinite series, x goes from 1 to infinity, x squared q to the x minus 2 power. There's our substitution. We're going to substitute that with 1 plus q upon q times 1 minus q. Okay, and so we get that from the second derivative of this series. So we're going to make use of the substitution to help us with the variance. So let's take a look. All right. So we have our variance of our random variable x, and this is going to be a geometric random variable, is the infinite sum. X goes from 1 to infinity. Now, the variance says x minus its expectation, e of x, quantity squared, times the probability p of x. Well, substituting for the probability mass function for a geometric random variable, that's the sum. X goes from 1 to infinity of x minus e of x, quantity squared, times, we're going to write that mass function q to the x minus 1 power times p. All right, so now let's do a substitution. Now we know that e of x is just 1 over p. So we're going to write, instead of that, e of x, we're going to say x goes from 1 to infinity of x minus 1 over p, quantity squared, times q to the x minus 1 times p. All right, so now we're going to do the square. So when we do the square, we're going to use the FOIL rule. Infinite sum, x goes from 1 to infinity. We're going to have x squared minus 2x over p plus 1 over p squared, all quantity, times q to the x minus 1 power times p. All right, so now we're going to distribute this multiplication by q to the x minus 1 times p over each one of these factors. So we're going to distribute it, and then we're going to separate out the sums for the first term, the sums for the second term, and the sums for the third term. All right, so let's do that. So we have the sum, x goes from 1 to infinity of x squared q to the x minus 1 times p. All right, so we write that, and then we have a minus our sum. X goes from 1 to infinity. We have 2x upon p, q to the x minus 1 power times p. And then we have plus our infinite sum. X goes from 1 to infinity of 1 upon p squared, q to the x minus 1 times p. All right. So now that we do that, let's do a little bit of algebra. And so for this first term, we notice that this p does not involve an x, this index of the summation. And then we can also pull out a factor of q for this multiplication of q by itself, x minus 1 many times. So if we do that, we're trying to isolate and get something with an exponent that's x minus 2 and not x minus 1. So we're going to take that first term, we're going to factor out a p, we're going to factor out a q, so we're going to write q times p, the x goes from 1 to infinity. We're going to say x squared times q to the x minus 2 power. Okay, so now in the second term, we notice, well, a p is here, and we have a p here, right? So p's in the numerator here, p's in the denominator. These p's cancel, and then we can also pull out this 2. So if we do all of that, we have minus 2 times the infinite sum. X goes from 1 to infinity. P over p cancels, so it's going to be x times q to the x minus 1 power. Okay, so now we have this 1 over p squared, and we have this q to the x minus 1 times p. So let's factor out this 1 over p squared. We're going to leave the other p there because we're going to take advantage of law of total probability. So we're going to write plus 1 over p squared, or infinite sum. X goes from 1 to infinity of q to the x minus 1 power times p. All right. So now that we have these terms, let's go ahead and do some substitution. Now, we just got done saying for our variance, when we did this double derivative, the second derivative of the infinite series, we said that was equal to this s double prime of q was equal to 1 plus q over q times 1 minus q to the 3 power, right? So we're going to use that substitution. And that substitution is what we use when we have an infinite series. And it was a definition for x goes from 1 to infinity of x squared q to the x minus 2 power. We did that on the previous slide. There was our result from the second derivative applied to the formula version of the series. All right, the geometric series. Okay, so we're going to make that substitution. So we get q times p, and we're going to now substitute. We have 1 plus q upon q times 1 minus q quantity cubed. And there's our substitution. And so the next thing we're going to do is we're going to make a substitution that we got when we had the first derivative of that sequence. From the previous slide, we had the first derivative. We found that we had this infinite sum, x goes from 1 to infinity, of x times q to the x minus 1 power. We can substitute that with 1 upon 1 minus q quantity squared. So we're going to make that substitution right here. So we're going to write minus 2 times, and we're going to have a 1 upon 1 minus q quantity squared. Okay, so there's our second substitution. And then lastly, if we look at this term, that's exactly the sum of all the probabilities across all of the instantiations of our geometric random variable, and that goes to 1 because of log total probability. That's what we just showed. And so here, this is going to go to 1, and we're going to write plus 1 upon p squared. All right, so now that we get to this step, the rest is just some algebra. And so we're going to observe here, we have a q in the numerator, a q in the denominator. So those are going to cancel. And we write p times 1 plus q over 1 minus q to the 3 power. This second term, that's the first term, second term, we have 2 over 1 minus q quantity squared. And then that third term is just 1 over p squared. All right, so now what we're going to do is we're going to combine these first two terms. Now, the first term has a denominator of 1 minus q cubed. The second term has a denominator of 1 minus q squared. So if we find the lowest common denominator, well, that lowest common denominator is 1 upon q cubed. So we're going to write p times 1 plus q minus 2 times 1 minus q all over 1 minus q quantity cubed. And we still have that plus 1 over p squared. So if we reduce the numerators here in this first term, well, we have p plus 1, p times 1 plus q, right? P times 1 plus q. And then we know that 1 minus q is the same as p, right? So we're going to write minus 2 times p. And 1 minus q is p. So we're going to say over p cubed. And then we're going to add our second term plus 1 over p squared. All right. So now that we've done that, we're almost done here. We're going to combine these two terms. The lowest common denominator is p cubed. Here we have a p squared. So that's going to become p times 1 plus q minus 2p upon p cubed. And that next term is going to be a minus p. Okay. So now we put them all together. And if we put them all together, that gives us minus 2p minus p. Well, that's p times 1 plus q minus 3p over p cubed. All right, so now if we factor out a p out of the numerator, that's equal to p times 1 plus q minus 3. Oh, you know what? There's an error. So that should say plus p, and that should be minus p here. Minus p. There we go. So that's minus 1. Okay, knew there was something wrong. All right, over p cubed. All right, so now we have that's equal to, let me start down here, p times q is 1 minus p, 1 plus 1 minus p, that's our q, minus 1. That's going to be our numerator. Okay, and our denominator is still, is still p cubed. Okay, so now we factor out p in the numerator, p in the denominator. So that's 1 plus 1 minus p minus 1. 1 plus 1 minus p minus 1 over p squared. Okay, so we have 1 minus 1, that's 0. That's 1 minus p, 1 minus p over p squared. And this is our result. So the variance of our geometric random variable is 1 minus p over p squared. And that's exactly our solution that we had. And so the key is you take your geometric sequence, you take the first derivative, and you use that solution for both the first derivative of the closed form for the geometric sequence as well as the formula. You use that as a substitution to help you solve for the expectation. Do the same thing with the second derivative of the closed form for the geometric sequence and the formula for the geometric sequence. You use that to find a substitution for this infinite sum, sum of x squared times q to the x minus 1. And then you use that in a substitution for your variance expansion, and you get your solution, variance is 1 minus p upon p squared. Okay, so that's a little bit of a mouthful. I just wanted to make sure to do all of that solution. I don't like how the book presents it, so I thought it would be of value to spell it out each step along the way. All right, so with that, that's all I had. Gave myself plenty of room. Next time, we will focus on more families of distributions, mainly, specifically, the negative binomial and the Poisson distribution. So with that, as usual, please stay healthy, stay safe, and I will see you all on Tuesday.